Okay. Good morning, everyone. And I would like to, before I go into the details, this is a work that I've been doing with Peter over the past 1.5 years. Yeah, I would like to say something about Peter before going into the meat of this work. So the first time that I met Peter was in 2019 at the CM conference in Toronto. And at the time, I was a PhD student at Bates Business School, what was called like before CAS. And like I was doing compound derivatives, so essentially compound option with application to credit risk, which is like a topic like the interaction between credit risk and option prices that Peter had worked extensively on. And so what I did at the conference was like stalking him. And I think it was like he had two talks. One was in the plenary session, which was, I would say, the archetype of what I'm going to present today. And at a second talk on the parallel session. And at that time, I tried to speak with him, like discussing with him my research. And like to my greatest surprise, he was like the nicest, probably the nicest person that I've met, like in academia, and at the same time, probably the most competent also. And so it's extremely sad what happened. And I feel like it's been a privilege to have had the possibility of working with him. And I've learned like over this past year that we work together a lot from him. So I will be always thankful for this opportunity. And so let's go to this idea. So essentially, there is a paper by Carr and Torricelli from University of Bologna, and that I will refer to, that develops two alternative models for pricing option in the way that it's elementary. Elementary refers to the fact that you don't need to use any special functions. Essentially, it's the idea that you can use an high school calculator for pricing an option, which is quite remarkable, I think, if you think that the standard way of teaching this is Black-Scholes, and best case, at the end of the book, you have the tables of the normal distribution. I have all the students like doing the calculation and interpolating between things. So as in the next slide, the idea, there is like this model that Carr and Torricelli have developed for pricing vanilla options that doesn't require any special function. And as like during my PhD, I studied compound options, so options on options. The circumstances, like I attended a talk that Peter was giving online at Bates, so organized my previous supervisor, Professor Ballotta. And at the end of the talk, I asked a question to Peter about something, because he was presenting a talk about a type of compound derivative. So I asked him a question. I guess he understood that I knew the topic, and then we started working together. So in this specific talk, what I'm going to do is see if there is a way for pricing compound derivative under this new set of distributions that will still remain elementary. And then if further you can apply this for the pricing of essentially of the well-known Whaley formula for the pricing of an American call option on an asset that pays a non-discrete dividend. So for the literature, what we have here, it's essentially the work that I mentioned before, the Carr and Torricelli paper that is on finance and stochastic, where they develop consistent, a class of distribution for consistent risk-neutral pricing that ends up in option pricing formulas, which are elementary. And here we investigate if this can be extended to the pricing of compound derivatives. Let me just remind you that compound option, despite not they are not a traded asset, but they are used for like modeling other important problems in finance. So if you standard Merton, you see equity as an option on the firm asset, then equity options becomes compound option. And at the same time, in structural default model, you can price equity, as I said, Merton, Jeske, as compound options. American claims are to some extent priceable in some specific cases using compound option, as well as some other exotic derivatives. So this is the main purpose of working with compound options. I will give a brief, sort of brief, introduction to this class of distribution, since I think most of you are not like super familiar. Like when I started working with Peter, I wasn't. And so I think it's good that we are all on the same page. So the first and main building block of this idea is this distribution, which is called the Dagum distribution, which has this PDF and CDF that you see on the screen. And especially this is a 3-parameter distribution where M for some cases represent the location, and in some cases the mean of the distribution. It is the mean when the parameter P is larger than 1. If P is less than 1, then the mean doesn't exist, as it becomes infinity. P controls the precision, which is the same thing as saying that 1/P controls the dispersion of the distribution. And I think the nicest, like why using a different distribution? Well, an interesting part of this distribution is that this parameter Q controls the skewness. And the fact that you can change the skewness relatively easy of the distribution, I think is relevant for financial returns, which are like notoriously, they display negative skewness. So for Q larger than 1, you would have this negative skew in the log of this distribution. So this is the building block. Then the next slide is about 2 other random variables that are connected with the Dagum distribution. One is the skew-logistic distribution, which is essentially the distribution of the log of X if X is Dagum. And the Singh-Maddala distribution, which is the distribution of 1/X once X is Dagum. So apart from having like the formulas on the screen, which I mean are important, but I mean they're just a PDF and a CDF. And let me say that why they are relevant. Well, they're relevant in a sense because if you believe the thing that I forgot to say before, sorry, is that this is a variable which is defined over the positive real line, which means that this would be the variable that you can use for describing prices. Okay, so then log becomes like a measure of return, or at least log prices. And then 1/X, it's interesting in this set of distribution, because the Singh-Maddala distribution somehow will enter into a change of measure that we do for the pricing. It's not over, because what we are going to work with are not just this like Dagum, Singh-Maddala, and skew-logistic, but we're going to work what we call conjugate-power Dagum, conjugate-power skew-logistic, conjugate-power Singh-Maddala. And they're called conjugate because what we do is that the parameters P and Q are all their conjugate. And this, first of all, reduces the number of parameters, because then you would have just a 2-parameter distribution, which you have M and the notation of the slides B. And again, you would have that since that P in this case it's larger than 1, the mean converges and it is equal to M. Since the Q is larger than 1, you have that the ln, the natural log of X would be negatively skewed. And in the paper of Carr and Torricelli, they also show that this Dagum distribution shows mild excess kurtosis. So all these 3 are features that we would like to be able to model, like when we look at financial returns, I think. So it's interesting that we have a distribution that accommodates for all these 3 facts: finite mean, negative skewness, and mild excess kurtosis. as well as it is a two-parameter distribution, and we know, like, we are able to write explicitly both the CDF and the PDF. So having said this, we go to the actual talk and like the proof and the derivation of everything that is in the paper. So usual assumptions, we work with a filter probability space. We assume the existence of the equivalent martingale measure, and as well as in the same spirit of Carr-Torricelli, we have assumed zero risk-free rate without loss of generality. And we further assume that the price at maturity of the underlying asset is distributed under the risk-neutral measure as a conjugate-power Dagum random variable with mean S0 and bewilderment parameter BT. So as you would have, is that for each maturity, you would have a different B, and you are able so to have a term structure of what, I mean, B is not the volatility, okay? In fact, it's called bewilderment. And, but at the same time, in the paper, Carr and Torricelli show that a possible way is not like unique. There are other possible parameterization, but I think the simplest one is in the formula that you see at the bottom of the slide, because this function only needs to satisfy some very simple requirement. It needs to be bounded between 0 and 1, as well as it needs to be vanishing as the time horizon shrinks. So these are the only two requirements that are indeed like required for having this to work. So, but like in the paper, I don't have it in the slide here because it's going to be like, there's going to be some meat here. So, but what I do in the paper, I'm using this specific parameterization to map volatility with this bewilderment parameter. So what I'm going to do next, I will first show you how you price the merit put. This is not new, like it is the same, like this is the same result that is in Carr and Torricelli, but I do it in a different way. I do it with a change of measure, which is relevant for what I have to do next when I move to the pricing of the compound derivatives. So, sorry. But before doing that, let me convince you that this is consistent with risk-neutral pricing. So since we assume that it is a zero risk-free environment, we want just to show that the mean of ST is indeed S0. And in fact, if you do the computation, you plug in the PDF of S, which is again conjugate-power Dagum. You solve the integral, you do your math, and in fact, the integral is equal to S0 as long as B is between 0 and 1. So we're good to go from this point of view. And then we move to the merit put. So the merit put is nothing but the maximum between a random quantity, ST, and K. It is the familiar portfolio that you would have talking to student when you have to prove the put call parity. Is the call plus the cash, or the put plus the underline, and this is why like Peter named it merit put, because it's the put plus the underline. This is a funny, I don't know if it's funny, I thought it was funny, and Peter laughed when I make this joke that an alternative name of this could be the divorced call, because it's the call plus the cash. So, but this was just me being silly with him. So essentially, you can, as you know, what you need to price for pricing calls and put is just the value of this portfolio, and then you will find the value of the derivative accordingly, just like with the bottom subtracting the stripe or the underline. But nonetheless, like up to, this is quite general. So if you assume that we have an equivalent martingale measure, so we assume that there is completeness, and you assume that the underline is traded. So thank you for the nice talk about non-traded assets before, because it was a nice refresh in terms of this. So you can also do another change of measure. You can do the change of measure which you see in 1, which essentially you are changing from the risk neutral measure to the spot measure, so the one that has S as a numerator. So, and so equation 1 is very general. Like you would use 1 when you use Black-Scholes, like log returns that are normal distributed, but you can do the same under this other class of distribution. So what I'm going to show now is the familiar result that you have in Black-Scholes. So what you normally assume is that the log returns or the arithmetic returns are distributed as a normal random variable with some risk neutral mean and sigma t. And you know that under the spot measure, what you do is just essentially you are shifting the mean of the distribution. You just change the change of measure, like just affect only the location of this random variable, not the dispersion, and the distribution remain unchanged. So you just can compute the two distribution, the two probabilities. But as you see, this is not elementary. We have the special function, the CDF of a normal distribution, which is involved into this. And the whole purpose of like this work is indeed showing that maybe there is a more natural, a simpler way of pricing option than this. And at the same time, if you're able to do so with a class of distribution that accommodates for other relevant stylized facts that you observe in returns, I think is a win-win situation. So on the other hand, we need to first look at the distribution under the share measure when you have the conjugate-power Dagum. Because it's not like normal distribution, like it's very easy, like it's the easiest that you can think of in terms of deriving some results. Probably the final product is not the easiest to read. I mean, you could have a easier one, which is the one that we discuss here. But the normal distribution allows you, and this is something that I realized very much while I was like finishing this paper, and that the beauty of the normal distribution is that it makes things a lot easier. And when you work with other distribution, well, you have to be, you don't have to take many things for granted, like many things that work for the normal don't work for the other. So nonetheless, the way you would price this under this spot measure, this is just a, notational trick, I would call it. Essentially, what you have on the numerator is the expectation of S times the indicator function, and that's it, divided by S0, which you would multiply when you do the change of measure. So it is essentially the Lorentz curve of the CDF, but nothing very special. It's just to say that for having the CDF of ST under this alternative measure, you just need to compute the integral and divide by 0. And if you do so in the conjugate-power Dagum, you are able to solve the integral. And what it ends up is that the CDF is indeed the one of a Singh-Maddala. And so you see that there is, so in the Black-Scholes world, when you change the measure, you retain the same distribution, you just shift the mean. While in this case, when you change the measure, you keep the same parameters, but you change the distribution, which is what's very fascinating to me. So if now that we know essentially how to compute, Q hat, we know how to compute Q. You can plug in the first one is the survival function, and the second one is the CDF. You do a little bit of math, and then you get to the result, which is in Carr and Torricelli. So, and I think this is extremely beautiful. I really think like that there is some innate beauty in this, because essentially you're saying that you can price option just with an LP norm, which at the same time, like, this was when I said, like, this is the continuation of what, like, the first time I met Peter, it was presenting essentially this result without distribution. Then he looked for a distribution that was able to produce this result. But the general idea, and if you think about it, I think it makes a lot of sense. Like, at the end of the day, a married put, or let's say a call option, is like, if you look at the payoff, it is a flat line and then a 45-degree line. So, And we know that this is the payoff at maturity. And we know that the option price before maturity is going to be a convex function that the more you go towards maturity, the more it flattens and becomes this straight and 45-degree line. So I think that Peter thought, okay, what is the largest class of functions that I know there will be convex, and then in the limit, they will become this flat and 45-degree lines. And I think that the beauty of this formula is that, well, the answer is the LP norm. Because even if you think so, the L infinity norm is the max function. So there is a smooth connection between the two. So it shouldn't be that surprising. I think the interesting part that Peter did with Lorenzo was finding a distribution that is able to produce this, and like they found it, and that's it. So at this point, I think I set the ground for convincing you that you could price options under this model just using an LP norm. What we do now, and this is the main contribution that I work on with Peter, because like so far there was just this change of measure that when you do the, like in the appendix of the paper, there is a, I would say, a thick part about the change of measure and how to do so. But what we're going to do is looking at compound merit puts. And compound merit puts are connected to compound option, and like the next slide, I will show you how to connect them. But since the simplest formula that you can get for pricing options is the one of the merit put, Peter told me, don't work on the compound colon-call, on the colon put, work first on the compound merit put on merit put, because the merit put is the easiest thing that you can price in this model. So I started work on this, and essentially it's just a max on a max. So you can easily show that the price by resistance evaluation would be given by the expectation of the merit put at time t1 times the indicator function that this merit put at time t1 is larger than k1 plus k1 times the probability, the risk neutral probability, then the merit put will be below than k1. And as the merit put is an increasing function of its argument, well, then there is, this is very, like, if you have worked with compound options, this is like standard in a sense, like that you can find a critical strike K star, which reads in the same way as K1. So essentially you are moving the problem from the derivative space to the underlying space. Since you know the distribution of the underlying, this makes life a lot easier. And let me tell you that in general, so for it's again very general. You can apply to different sets of distribution. I will do it with like usual Black-Scholes and then with our distribution. K star is model dependent, and the fact that the one that you have in Black-Scholes has to be found numerically. The one that you will have under this distribution is instead elementary. You can find it and write it explicitly. One thing that I must assume for going further is that we are working with what I call the symmetric compound merit put. So I have to assume essentially that we have like a longer maturity, and then exactly at half of this time length, there is the underlying merit put that kicks in. And the reason for doing so is essentially because I need to have the same bewilderment parameter. The bewilderment parameter depends on the time horizon. And so if you have different time horizon, you would have different B's. And it's just a simple, like, at least at this point, but I still think it's very difficult unless you impose a very convenient structure on this function B, that many of the calculations simply do not work if you have different B's. So for the purpose of the talk, just think of as like this underlying merit put expiring in exact half time of the total maturity. And for the final application of the American, I think this is also gives some, I mean, of course, I would be happier if I could do it for any T's. This is maybe for the future, but I can easily, I think, at least identify the case where this is. So what happens in the normal case is this very simple thing, that the sum of normal is normal. So essentially, what you need is the distribution at maturity. If the increments are normal, the distribution at maturity is normal, and you're fine. You're just plug in, you do the things, and you would prove that the price of the merit put will depend essentially on the bivariate cumulative distribution function of a two-dimensional normal vector with a given correlation parameter. And this is, I mean, this is merit put, but if you just, as you will see later, you connect this with compound options, essentially this is the Jeski formula for the price of compound options. What happened in the conjugate power Dagum is instead something that, oh, another thing, which, so in the normal distribution, we think of log returns and because they are additive. And on the other hand, here we will work with geometric returns, so with price ratios. So in this setting, essentially what I assume is that we have a multiplicative random walk with parameter b and mean 1. And of course, in this case, the product of this is not conjugate. So part of this is also finding what is the distribution of the product. This is done in the paper. I will not explain you this here. The important thing is that the two period merit put is not the LP norm, okay? But the one after one period is, and this is the only thing that I need. You can find the value k star, and you can compute essentially the integral. Like you have this expectation, and this is the result, the integral that you need to solve. And this is the main, the main technical result. This integral can be expressed first in terms of a special function, which it was, at least to me, very obscure because I've never found it in finance. It is the Appel hypergeometric function, which essentially is a generalization of a bivariate hypergeometric function. If mu is equal to m, which essentially in the case of option will mean that the underlying merit put is at the money, this collapses to the hypergeometric function. And in particular, if the parameter b is a half, then the integral is elementary and it is just a function of the arctangent. You put everything together and you have the pricing formula essentially, which, I mean, it's not super nice, but for some parameterization, it is the one that you see at the bottom, which is indeed elementary. There are no special function. You can calculate this with a calculator. That's the idea. And there is no such parameterization, no matter how you look for it in the Black-Scholes model, so that it would reduce to an elementary function. I will skip this part. This is just simple things where you do the math and show that how to connect essentially merit put to compound options. So if you read the last line, like the merit put is a call on call plus cash, or it is a put on call plus a merit put. Let's go to the final result because time is running up. So this is the Whaley decomposition. They show that if you have an option, a call option on an asset that pays a discrete dividend, known discrete dividend as a given time, you can replicate this with a portfolio of 3 options. A call option on strike K star, where K star needs to be determined and maturity is 1. A call option with strike K2 and a maturity T2, and a call on call. Given like at this point, you would have everything that you need to price this, because I gave you like the pricing formula for the call on call. So you could just apply the formula that I've given you and have essentially the equivalent of the Jeski-Whaley formula under a different distribution. But that's not the point, because you see the general is not elementary. I want to show you that there is a parameterization for which this turns into elementary. So Roll shows that the way to find K star is by solving that equation, which means solving this other equation that for some values of B is elementary. So for B, a half, a third, a fourth, and a fifth, like you would have this to be elementary, and at the bottom you have the two values for a half and a third. Of course, for a fourth and fifth, it becomes more and more cumbersome, but the one that I will be using here is a half. So the first expression that you see here. And then essentially I rewrote the price of the American option in terms, rather than of calls and calls on call, in terms of merit puts. So if you plug in everything, you end up with the chunky expression that you have in the center of the slide, which is not elementary yet. To have it elementary, we need to have the merit put on the merit put to be at the money. So essentially, we need to enforce condition 9, which means that like this formula becomes elementary for a very specific value of the dividend, which in the specific case is 2 minus square root of 3 S0. It comes up just solving the equation. And then you do the math and you would get this formula that at this point, it's still elementary. But if you do some math further and you are able to show this, and essentially this reduces just to the formula that this option for B1/2 and this specific value of the dividend is 3 plus pi over 3 minus 2 square root of 3 times S0, which I think it's quite at least remarkable, because it is an American option, and you are just like it is a multiple of the price of the underlying today. Of course, these are like very like specific parameterization, but the whole point is that there is no other parameterization in Black-Scholes that this formula would ever turn up to be elementary. And I leave you, like, I think I've talked over time, so I will thank you very much for your attention.
Thank you for a very elegant presentation. I think a lot of option pricing professionals will be out of work with those simple formulas you're putting up there. We don't want to let that out of this room, okay? So, please don't let anyone have these secrets. Any questions for us? Let's squeeze in one question, because we are running a little over time. Anyone want to ask a question?
First of all, very interesting presentation. That I have a question indeed on the formula for approximating American. So one of the nice things, I guess, of the Roll model is that you can also have multiple, at least more than one dividend, and the multivariate Gaussian will become just 3-dimensional, 4-dimensional. Have you looked into extensions or something like that? Or you have any intuition?
I've tried. And the problem here is the following, that like, and the whole problem relies, sorry, here. I get that here. So to have the distribution at maturity, you need to look at the product of these two quantities, which is not conjugate, but still I can express the CDF. So it is a random variable, which I know the CDF and the PDF. If I have to do, let's say, another, so I have to do another multiplication, I have to do another integral, and I haven't explicitly tried, but because I didn't want to. It's like, you start with something which is very cumbersome that for some specific parameterization, I would say almost magically becomes super simple. But I mean, there was a lot of like sweat in finding the right approach to tackle this problem. And I think that unless you find a very magic, I would say, expression for B, where you can actually insert in and somehow arrange it to make things work, it becomes very challenging. And yeah, so, and the fact is that here, essentially what you do when you do the normal stuff, like the normal distribution, you work with Fourier transform, essentially. You transform sums into convolutions. What you have to do here is something that is not sums. You have to transform products into convolutions, which essentially means you are not using Fourier transform, you're using what's called the Mendes transform, which again, it's not as studied as the Fourier transform, but I mean, you have to find very specific case for this to work. Thank you very much.